All right. If we talk about kinematics, which was the previous chapter, that one was about the study of motion without considering the forces that cause that motion. Now, in dynamics, you are also talking about motion, but this time you're more interested in knowing the forces that cause that motion. All right. Both the previous chapter and the current chapter will both talk about motion in general, but the previous one, kinematics, was more interested in you describing the motion, but you don't really consider the forces that cause the motion. This chapter is also about motion, but you're more interested in knowing the forces that cause that motion. Okay, so we'll start off with the first thing you need to know, which is linear momentum. That's often denoted by a small symbol P. Momentum is actually the product of mass and velocity. In IGCSE, you will have learned this already. Any moving object would have momentum, and it is normally found by calculating the product of mass times velocity. Now, momentum is a vector quantity as it has a direction associated with it. Now, there are a lot of questions that would normally ask you, if let's just say I have an object of mass m, it hits something like, let's just say the ground, and then it rebounds, both with velocity v before and after the collision. They ask you, what is the change in momentum of the object? Now, when it comes to finding the change in momentum of the object, you will realize that when this object of mass m, say this is a ball, was moving downwards, it had a momentum of, initial momentum of mv. And then after hitting the ground and rebounding, it had a final momentum of mv also. Now, when you want to find the change in momentum, it doesn't matter whether you take the final momentum minus the initial or the initial minus the final. In general, you will tend to get back the same magnitude of answer. The difference is that you might end up with a negative sign. So let's just look at this one first. If I take final momentum minus initial momentum, now before you proceed any further with this, because I said that momentum is a vector quantity, there is a direction associated with it. Whenever you try to do something like addition or subtraction of vectors, you need to establish a sign convention. Recall that in the last few chapters I mentioned to you, when you're dealing with calculations on vectors, you normally need to establish something like a sign convention where you assume a positive direction. So it's the same case here. When finding changes in momentum, you need to have an idea of sign convention, which direction is positive, which direction is negative, so that later on you can consider any negative direction that is present. So say right now, if I'm looking at the first example on the left here, I take my sign convention as downwards positive. So if I say final momentum minus initial momentum, the final momentum is this. Notice that it is actually pointing upwards. It's actually upwards. This is opposite to my sign convention, so this is considered to be negative momentum. All right, so that's why I had a negative sign here. It's negative mv minus the initial momentum. The initial momentum here is in the same direction as my sign convention, so this is just positive. There's nothing I need to add to it. So this one I just take negative mv minus mv, giving me negative 2 mv. That's why the negative is here right now. Now, if I were to do it another way, like the ones that are shown on the right here, I take initial momentum minus final momentum. So as I said before, my sign convention is downwards positive. My initial momentum is positive, so it's just mv. But then minus off with final momentum, the final momentum is negative, so it's minus negative mv, giving me 2 mv. So magnitude wise, I'm going to get the same answer. In your exams, you don't really need to bother which one should be minusing the other. Just take either one, okay? But please make sure that you apply a sign convention to what you subtract, all right? A lot of times we're only considering the magnitude. We just want to see the magnitude. As long as you have a magnitude there and it's correct, that'll be fine. You having a negative sign there doesn't matter, okay? Then some other thing they may also ask you is that For the momentum change that you've calculated, what is the direction of the momentum change? Now here, direction of momentum change will always be in the direction of the force exerted due to the momentum change. Say what do I mean by that is that if you consider the examples just now where you have a ball of mass m, it drops downward and then it rebounds upward. Now, intuitively, you would know that the reason why this ball can bounce upwards is because there is a force exerted on the ball that causes it to move back outwards. All right. Your force F that caused the ball to move outwards was this. All right. Your momentum change is going to be the same direction as that force. All right. This is just something you need to know, because in the earlier past years, they tend to ask you this: what is the direction of your momentum change? So the key thing is to know that the momentum change is always in the direction of your exerted force. Okay, the one that caused the object to move in some particular direction. Okay, so this is just an introduction on momentum. So we'll move on to something else that you're supposed to be more familiar with. Now, you've learned Newton's law of motion. Newton's law of motion have three laws. Okay, the first one is Newton's first law, which tells you that a body remains in its state of motion, which is either at rest or moving with constant velocity, unless a resultant force acts on it to change that state. So what do we mean by that is something like this. If you have, say, a stationary object, okay, you have a stationary object. If you don't apply any resultant force on it, it will remain stationary. But if, say, that stationary object, you apply a resultant force on it, then this one will start to move. Okay, with no resultant force, your object will just remain stationary. But once you have a resultant force, this object will start to move. That one is for this part. Okay, it remains in a stationary state unless a resultant force starts to act on it. Then if I move on to another second case, say right now you have an object that's moving with a velocity v. Okay, let's just say v1. All right, constant v1, constant velocity v1. Now, if there is no resultant force acting on your object, this one will remain at the velocity. This one will. How should I put this? Let me just revert this for you. This one continues at constant velocity. Okay, so if say I have an object that's moving with a velocity v1 right now, it will continue at that constant velocity. But if say suddenly now I have a resultant force that acts on it, what will then happen is that the velocity changes. Okay, now it may suddenly change from v1 to v2. So this part here is that because you start to have a net force acting on it, velocity changes. Okay, so if I didn't have a net force, these two portions here, no net force, this one will remain stationary. This one will continue at constant velocity. But the moment I start to have a net force acting, a stationary object will now start to move. An object that was previously at constant velocity will start to have its velocity changing from one value to another. Okay, so the first law here implies that all matter has an inbuilt tendency to resist any change in its state of rest or constant velocity. You have something that is resisting a change in its state of motion. This is called inertia. All right. So inertia is the property of a body that resists changes in the state of motion. Now, inertia can be measured by mass. The bigger the mass of a body, the bigger its inertia, and hence the greater resistance to its change in velocity. All right. So specifically what do we mean by that is this. If you take, for example, someone that is running towards you is a little kid, all right? Just say that this is a little kid whose mass is maybe 10 kg, all right? Now, if that kid is running towards you and you want to stop that kid, you will say that it's easy to stop that kid from running to stop that kid from bumping into you. But if I issue another separate example, this one is an adult, a very large adult, whose mass is probably 120 kg. Okay, so same thing here. That guy is running towards you. So if I ask you right now, between stopping this kid and this adult here, which one is easier to stop? You will say that it's the kid, right? Yeah. Because here the kid has a smaller mass, all right? He is currently moving. You want to stop that kid. You want to change his state of motion. So because his mass is smaller, it doesn't take much to stop that kid from moving further. All right, that is what inertia is, in a way how we illustrate inertia. Okay, so if the kid is moving, you want to stop that kid from moving, you will say that it's easier because he has lower mass. But on the other hand, if you want to stop this adult here, there's a mass of 120 kg, you will say this one is considerably harder. You will have to exert a lot more force, a lot more effort to do so. Okay, the reason why is because this guy has more inertia. It is harder to change his state of motion. Okay, so that is what inertia is in relation to mass. You will intuitively know that if something has larger mass, it is harder to stop it from moving. It is harder to make it move in the first place also. Okay, so Newton's first law is sometimes called the law of inertia. All right, so this one is Newton's first law. Okay, then we move on to Newton's second law. Okay, now Newton's second law in IGCSE, you may have learned Newton's second law as F net equals to ma. The first thing that comes to mind when we talk to you about Newton's second law is that F net equals to ma. Now, this one is only partially true. Okay, this is not the full definition of Newton's second law. In IGCSE, if you had used this one would have been considered as correct. But now in A levels, this one is not the definition of Newton's second law. Newton's second law is actually defined as this. The rate of change of momentum of a body is directly proportional to the resultant force acting on it and takes place in the direction of the force. So in your exam questions, when they ask you to define Newton's second law, they typically allocate 2 marks for it. The first mark is you saying this: rate of change of momentum is directly proportional to the resultant force acting on it, and it often takes place in the direction of the force. This is your second mark. Okay, this is the definition of Newton's second law. If you use resultant force equals to the product of mass times acceleration, this is wrong. This is not Newton's second law. Actually, F net equals to ma is a consequence of this definition. It is the effect of this. All right. So what do I mean by that? We will see in the later parts here. Now, if you just look at the word definition for Newton's second law, written in equation form, it means this: resultant force is directly proportional to rate of change of momentum. Okay. And then after that, you learned before this that momentum is mv. So P will change to mv here. So F net is directly proportional to dmv over dt. Okay. Now, if you have a case of a body of constant mass, this m can be taken out. So you just get F net directly proportional to mass times dv dt. Okay. Now, F net being directly proportional to mdv dt, you want to get rid of the proportionality sign here. You learn that in maths, when you want to get rid of some sort of proportionality sign and make it into an equal sign, you have to introduce a constant. So right now you introduce a constant k here. So F net is equals to km dv dt. All right. And then after that, you also learn in your kinematics chapter that dv dt is actually acceleration. Okay, dv dt, you can just think of it as delta v, delta t. Okay, they mean the same thing. All right, so your final expression becomes f net equals to kma, where k is some sort of dimensionless constant. Now, we normally define 1 Newton as the force acting on a kg of mass that produces an acceleration of 1 meter squared. So if you were to sub it inside that equation just now, F net equals to kma, this one is 1, this one is 1, and this one is 1. So obviously k is just going to be 1. Okay, so your k is actually just some sort of constant that is equals to 1. Eventually, your expression becomes this, F net equals to ma. Now, this entire thing looks like it looks like a derivation of F net equals to ma, but this one is not tested in your syllabus. Okay, you don't really need to bother so much about knowing in detail this derivation. What is important for you to know is that Newton's first law is defined as this, and then as a consequence of it being defined as this, you get F net equals to ma. F net equals to ma is a consequence of this definition. It is not the definition of Newton's second law itself. All right, so I already written it here. F net equals to ma is not the second law. All right, and it's also only valid for body of constant mass. Okay, so you see, why do I say it's not the second law? It's because it's valid only for body of constant mass. For the case of the Newton's second law that is defined for you, the rate of change of momentum is directly proportional to the resultant force acting on it. This one here, rate of change of momentum is this. Okay, this is what you call as rate of change of momentum. Okay, now you see, because we define P is equals to mv, you see, we will say that momentum changes when either mass or velocity changes. Okay, specifically we define rate of change of momentum as being directly proportional to resultant force. Rate of change of momentum is this. Okay, but because momentum has two terms associated with it, either mass and velocity, so momentum is considered to have changed if mass changes. Momentum is also considered to have changed if velocity changes. So the case right now was that you assume that mass was constant, only velocity changed, which in turn got you this one. All right. There will also be some cases where velocity is constant but mass changes. In that case, you will also have a resultant force, but that one is not represented by F net equals to ma. So this statement here, which says that F net equals to ma is not second law since it's valid only for a body of constant mass, this one is actually, as I mentioned, just part of the story. The Newton's second law, which talks about rate of change momentum, considers change in momentum due to mass change and also change in momentum due to velocity change. F net equals to ma only considered velocity change and mass being constant. There's still another case that is not taken into account. That's why I say this is F net equals to ma is actually just part of Newton's second law. It's an effect of Newton's second law. All right, so that one is okay. Now, another thing that you will need to know is this. This one is a very important fact. Resultant force and acceleration will always be in the same direction. You can see from here that F net is equals to ma. Mass is a constant here. That means F net is proportional to A. F net will cause A. And F net and A will always be in the same direction. You will never ever have a case where resultant force and acceleration are in opposite directions. They must always be in the same direction. Okay? And then the next thing you can talk about is force. All right. Now force is defined as rate of change of momentum. Okay, you see F net is equals to ma here. You can also say that force is rate of change of momentum, delta mv over delta t. Okay, so same thing here is either mass change or velocity change. Okay, now because force is defined as rate of change of momentum, this would mean that the gradient of a momentum time graph will give you force. What we mean by that is this. If you look at the diagrams below, you will see the diagram on the left, this one. This is a momentum time graph, and the graph varies like this. Okay, based on what we see here, we say that since force is rate of change of momentum, delta p over delta t, if you have a gradient, if you have a momentum time graph, the gradient is actually the force. You see, if I look at this point here, the gradient of this tangent here is change in p over change in t. All right, this one divided by this is rate of change of momentum, which in turn is equals to force. So that's why we can say that gradient of a momentum time graph is equal to force itself. Okay, so you will get questions like this where they give you a momentum time graph and then they ask you choose points on the graph which gives you the largest force. You're supposed to know that you need to pick the largest gradient. Okay, and then similarly, since we define force as rate of change of momentum, change in momentum is just going to be force times time. Okay, so if change in momentum is force times time, this tells us that area under a force time graph gives us change in momentum. So same thing here. If we have a graph of, sorry, there's a typo error here. If you have a graph of, no, this is not, sorry, this is not a typo error. This one is another momentum time graph, but this one here is showing you constant gradient, constant force. This one here, I said changing gradient, changing force. Okay, so there's nothing wrong with this. Area under force time graphs gives you change momentum is actually this. Sorry, it's actually this example here. Okay, if you're given a graph of force versus time, finding the area under the force time graph will give you the change in momentum. Okay, so these are just some of the key things that you need to know. All right, so the things that is not really important for Newton's second law is this one. This one, not important. It's something like a derivation. Nobody will ask you about the derivation in your exams. But the ones that are highlighted in yellow is something that will be tested in your exam. You're supposed to know this. If you don't know this, you cannot answer the questions. Right? So that is Newton's second law. Okay, then we go to Newton's third law. All right. Now, Newton's third law, you would associate it with equal opposite forces. All right. So specifically, we will say that for Newton's third law, when two bodies interact, they exert equal opposite forces on one another. There will be an action-reaction pair of forces under Newton's third law. But for this action-reaction pair of forces, you need to be careful a bit. All right. There are a few things associated with the action-reaction pair of forces. The first one is that they must be equal magnitude. Second one is that they must be opposite direction. The third one is that they must act on opposite bodies, two different bodies. And the forces, lastly, must be the same type of force. If it's gravitational force, it must be gravitational force. If it's electric force, it must be electric force for the action-reaction pair. If it's a contact force, it must be contact force. If it's magnetic force, it must be magnetic force for both the action-reaction pair. So to illustrate what we mean by that, there are some diagrams here that show you examples of Newton's third law. If you, as I say, you have a car that's on the road, the car is moving. what will happen is that as your car wheel turns, the tire pushes on the road, and in return, the road pushes back on the tire. So therefore, you have these two pair of forces right now. Sorry, this pair of forces. And then let's just say you have a rocket. The rocket is moving, it's flying through the air or space. So what's happening here is that when the rocket burns the fuel inside its fuel tank, the rocket will push out some gases. And in return, the gases will push back on the rocket. So this is Newton's third law in play. And then if let's just say you look at the two examples below here, you have an end pole of a magnet and another end pole of a magnet. So what you can say is that this end pole, sorry, maybe I use a different color. This end pole will repel this end pole. In return, this end pole will repel the other end pole. So this is action-reaction pair. Okay. Likewise, I can also say the same thing when I have two opposite charges, a positive charge and a negative charge. So what I can say is that this positive charge will attract the negative charge towards it. And in return, this negative charge will attract the positive charge towards it. So this is again action-reaction pair. And then lastly, if you have something like this, the lady that is pushing onto the wall here, the lady is pushing onto the wall, she's exerting a contact force on the wall. In return, the wall exerts an equal opposite force back onto the skater. Okay, so this is Newton's third law. All right, and then you look at the example of the ball that's being released downwards. So you have a ball that's being released. Now, you learned previously that if I were to release any object in Earth, the object will fall downwards because there's the pull of gravity on the object. The pull of gravity here, or rather the gravitational force on the object, is actually known as the weight, which is defined as the product mass times gravitational acceleration. This is the pull of the Earth on the object. Okay, so the reason why you have this force W here is because the Earth is pulling onto that object. So if you were to try to apply Newton's third law here, the Earth is exerting a force to pull the ball downwards. That force is what you know as the weight. According to Newton's third law, this ball will also exert an equal opposite force back on the Earth. So if let's just say right now, the force is the weight W here, the ball will also exert a force equals to W back onto the Earth. All right, that's what you're seeing here. The ball right now has an action force. The Earth is pulling onto the ball. And in reaction to that, the ball will pull back out onto the Earth. Okay. Now you may be wondering, if the ball is pulling up on the Earth, why isn't the Earth moving towards the ball? Instead, the ball is moving towards the Earth. Now, it has something to do with the mass. If you recall the equation, F net equals to MA, all right? Now, net, right now, this force and this force, they are equal and opposite. They are the same force. So F net is constant. That will mean that mass is directly inversely proportional to A. Now, if you're talking about the mass of the ball is very small. But you're talking about the mass of the Earth, it is very large. So from this relation that you see here, if I apply the mass of the Earth on this equation, because the mass of the Earth is very large, the acceleration of the Earth is very small. So here, although we say that the ball and the Earth both have forces exerted on them, you don't really see the Earth moving because the mass of the Earth is very large. That in turn causes very little acceleration, is negligible. But you compare with the mass of the ball, because the mass of the ball is very small, you have a very large acceleration. You can clearly see it moving. Okay, so this is the action reaction pair. Okay, now then I move on to something else. This is one common trick question that they would like to ask you in your exams. Now, if I have something like maybe this is the ground, and then I tell you that there's a block right now. On the block are two forces. You have the weight W, and then you have the normal reaction force R. The question that they will then ask you is that is W and R action reaction pair of Newton's third law. What do you think? Okay, right now we say W is equals to R. Okay, because this thing is not moving, right? It's resting on the ground. W is equals to R. But would it be correct to say that the weight and the normal reaction force is actually the action reaction pair of Newton's third law? Now, let's give you a hint. You look at the criteria for action reaction pair above the notes just now. There are some criteria that must be followed when you want to classify action reaction pair for Newton's third law. Okay, so let's go through this one by one. Can I say that they're equal in magnitude?
No.
No, this one I already say they are the same.
Okay, yes, sorry.
Yeah, they're not moving. If they're not moving, that means W equals to R. I can say that they are equal in magnitude, but are they opposite in direction?
Opposite as in like, can it be up and down or like just?
They're pointing towards opposite direction. One force is pointing in one direction, and then the other force is pointing opposite to what the first force was pointing in.
Yeah, opposite direction.
Yeah, okay. They're pointing in opposite direction. Okay, now acting on opposite bodies. Do you agree that R and W are acting on opposite bodies? In other words, different bodies?
No.
Let me just write this one. Opposing bodies can be different bodies. Okay, so this one here, you notice that R is acting on the block, W is also acting on the block, right? Correct? So
Yeah.
you see something is wrong here with this, there's a contradiction now. When you look at this example versus the condition for action-reaction pair for Newton's third law, you see that R is acting on the block, W is also acting on the block. So the case here is that R and W act on same body. Okay, so this is one contradiction that you're seeing here. R and W act on the same body. And then another thing is that if I look at the fourth condition, same type of force. So W, as I mentioned, is the weight. It's actually gravitational force. Okay. The R is actually what you know as contact force. Now, contact force is a force that arises when you have bodies in contact. Okay. Let me write somewhere here in a different color. Contact force arises when bodies make contact and push against each other. And push against each other. Okay, so right now, the R is actually what you know as a contact force. It arises when bodies make contact and are pushing against each other. All right, so R itself is contact force, but W is gravitational force. So if you look at the criteria for action-reaction pair of Newton's third law, this one is also not obeyed already because there are different type of forces. So what I can say here is also R and W are different types of force. So what conclusion can I then say? Is W and R going to be action-reaction pair of Newton's third law? No. The conclusion is no. Therefore, W and R are not action-reaction pair of Newton's third law. Okay. Now, then what actually then is the action-reaction pair of Newton's third law? Say right now, this is the ground, and then this one here is the block. Okay, let's say that right now what you're seeing is a snapshot of the block as it's falling to the ground. All right, it's not yet fallen to the ground. On the block, there is the force of gravity acting on it, which you know as W. Okay, now the force of gravity, the weight acting on the block, is a consequence of the Earth exerting a force onto the block. From what we learned just now, the forces must always be equal opposite pair. So right now, the block will exert an equal opposite force onto the ground, on the Earth itself specifically. You have an equal opposite force W. Okay, so both of these are gravitational force. This is actually the same as this. Okay, so far so good with this?
Yeah, sir.
So right now, what happens then when the block is now in contact with the ground? You still have the weight W on the block. You also still have the weight W on Earth. Let me just write it as Earth now. Okay, so this pair that you see here is still this pair. Okay, the ground is actually blocking the way of the block. All right, so because the ground is blocking the way of the block is now pushing against the ground. This one is the block is pushing against the ground with a force equals to W. Okay, this one, let me just run this as this. This is the force that block exerts on ground. Okay, this one is what you know as your contact force. Okay, right? There's a force that the block will now exert on the ground because the ground is blocking the way. Okay, the force that it exerts is actually equals to the weight itself. An example I can give you is something like this. If let's just say you're a person here, you stretch your hand outwards. This is your palm, for example. If you have a block of weight W, when the block of weight W makes contact with your hand, the palm of your hand, what you feel on your hand is a force of W acting on it, correct? Same concept here right now. Right now, the ground is in the way of the block. The block is trying to move towards the center, but because the ground is blocking the way, it can't move any further. So instead, it is now exerting a force that is equals to the weight onto the ground. All right. Now, as a reaction to that, your ground will now exert an equal opposite force back onto the block. That force is this force, okay, which is equals to W, which is what you know as R. Okay, so this one This is the force from ground on block. This one is what you commonly know as R, your normal reaction force. Let me just go through it again slowly. Before the block makes contact with the ground, you will understand that there's a gravitational force acting on the block, which you know as the weight. In return, the block will also exert a force back onto the earth with an equal opposite force. We can say that it's also another weight, force W acting outwards. This part is okay. But when the block starts to move downwards and it makes contact with the ground, the block will now start to exert a force onto the ground, which is equal to the weight. Okay. In return, the ground will start to exert a force back onto the block. Okay. F equals to W equals to R. We commonly know this as your reaction force R. Okay. So let me just circle the action reaction pair here for you. The action reaction pair of Newton's third law, one of it is this, the ones that I highlighted in green. This is the weight W on the block. This is the weight W on the earth. This is the gravitational force. Then after that, this pair here that you see is the other action reaction pair. This one is for contact force. Okay. Basically, what I'm trying to describe to you is actually this example here. Because you look at this one, you have a man that is standing onto the earth. You will agree that there's gravitational force acting on the man that is exerted by the earth on the man. In return, there's also an equal opposite gravitational force exerted by the man onto the earth. So far, this one is okay, right?
Yes.
Okay. But at the same time, because the man is in contact with the ground, he's pushing against the ground. Okay. When he pushes against the ground, he is exerting a force. The force that is exerting on the ground is actually equal to his weight. Okay, but let's not talk about that one first. We just understand that because the guy is in contact with the ground, he's exerting a force onto the ground. In return, the ground will exert an equal opposite force back onto the man. So basically, the action reaction pair is this one. This is the action reaction pair for gravitational force. And then this one is the action reaction pair for contact force. Okay. You will also have something called mass and weight. This one is something that you should know by now. Weight is the force of gravity acting on a mass in a gravitational field. It will tend to vary with location and is always directed towards the center of the earth or the planet that you're considering. Okay. Now, a free-falling body will always have an acceleration of g equals to 9.81 meters per second acting towards the center of the earth. When we say a free-falling body, just know that free-falling body only has the weight acting on it. Okay, when we say an object is free-falling, the only force acting is just the weight. So if the only force acting is just the weight, it will always have an acceleration of 9.81 meters per second. This one I showed you in the previous chapter before. If the only force acting is your weight and you have a certain acceleration as it falls, it will always be equals to g. Because that time I mentioned to you, F net is equals to ma. The resultant force is just the weight, and weight is defined as mg equals to ma. Here, the mass will cancel off, giving you a equals to g. Okay. So likewise, you're actually doing something in reverse right now. If you apply Newton's second law to a free-falling body, it gives the weight as mg. This one is moving with acceleration g. If you multiply with the mass, you're going to get the resultant force, which is in turn equals to the weight. Okay. Now, earlier I said that mass is a measure of inertia. It is the property of a body or object that resists changes in motion. Now, mass is independent of the body's surrounding. it will be the same regardless of the location that you are at. So there's always a comparison to be made between weight and mass. Weight will always vary with location, whereas mass will always be the same regardless of location. For example, if you have an object, you put it on Earth and you put it on the moon, we will tell you that the object on the moon will only weigh as much as 1/6 as it did on Earth because the force of gravity is weaker, but its mass will remain the same. So if your object is 10 kg, it will be 10 kg on Earth. It will also be 10 kg on the moon. But if its weight is, say, 100 Newton on Earth, its weight will be different on the moon. It's 1/6 of that. 1/6 of 100 will give you 17 Newton. Okay, this is what we mean. The mass remains the same regardless of where you're talking about, but the weight will change because the force of gravity changes depending on the planet that you're in.